Hi there, my name is Andres. As you can see, this is not a YouTuber setup. I'm not a YouTuber. I'm not a pro. I'm a developer with 25 years of experience, and I had a lot of trouble trying to understand dynamic programming, especially bottom up, because even though I grasped in the past 25 years ago data structures and some other stuff. Uh, Even having 20 years of experience doesn't give you enough context to understand the logic behind this concept of dynamic programming. So first of all, I'm not pretending to become a YouTuber, so this might be the unique video that I'm creating, but since I had a lot of problem trying to understand this concept, I just want to make this video to try to get to the point that I had to get to understand the why behind this concept. I want to thank Nico from Nico. I went through all the courses and examples from LeetCode. So I highly recommend you, if you haven't, just go and visit. I'm gonna put the link below. And so thanks, Nico. I just think for this specific topic, you focus too much on the examples and solving the problems instead of going back and just forget about coding. And this is about not forgetting about coding. It's just trying to make that click to facilitate you to understand the why. So I'm gonna start for the first thing. I'm gonna start is just one concept. Let me do this here. Okay, I think one of the biggest issues that I had to understand this concept was the wrong idea behind the naming. So it's a top-down is recursive solution, and bottom-up is using loops. So you need to iterate the loop, the problem and the input to solve the issue in a more efficient way, which is most of the time true. But here is the problem. So when you think about top and down, so most of videos and courses you will see, they'll try to explain that based on the inputs, based on the way that the loops are created, going from 0 to n, or going from bottom to top in like meaning in numbers. So from a lower number to a higher number, that's the bottom up. But for the top down, it's going from the top to the bottom, so which is top down. And it means in videos, it means that you are going from a higher value to a lower value, most of the time 0. But that's not right. So that was the base of the problem for me to understand the difference. So top down in reality is not related to the numbers. It's related to the way you use the base cases. So with top down, which is recursion, you go from the solution you need, so from where you need to go to the base case. So you go from the end to the beginning, to the base case. It can be, I'm gonna give you the best example, the climbing stairs. So you have this stairs here, and you need to go from 0 to n, right? So you can do the top-down approach, you can go from n. You can say, okay, I'm gonna go n. So n, let's say, is 5. So you're in the last step. So you can go one step lower and go in 5 or 3, and same here, 3 or 2, till you get to 0. So that's 5 to 0. It's like top down, right? But what if you do the opposite? What if you start in 0 and n is 5? What if you start in 0 here? And this means the steps you need. So you need to go here, okay, 1 or 2. And from 1 I can do to 2 or 3. And 3 or 4, doing 2 steps or 1 step. So this is also top down. You're solving the problem with creating sub problems every time. But 0 is not lower than the number 5, because 5 is gonna be your edge case. The edge case can be here when you get to the top. But you can also create the edge case based on the steps you have left or the steps you have taken. So it's not related to the numbers, but the way you start from the top to the edge cases, right? So same thing with if you create this with bottom up approach, you might do it the same way. You can start from 5 and decrement I till you get 0, or you can start from 0 and go up to 5, right? So it's not about the numbers, it's about getting from in the bottom up is going from the solution or the end of the problem all the way down to the edge case in the top down, and in the bottom up is going from the edge case all the way up to the finish. Not I minus minus or I plus plus. It doesn't really matter. You can do it in both ways, right? So now that I made that point, I just picked 4 problems here. Okay, let's try to make this better. So here are 4 problems from lead code, the number 70, climbing the stairs, house robber 198, decode waste 91, and coin change 322. So again, just please go and visit lead code and Nico.io, so you can have the whole solution. He will go from recursion, and it will explain how to implement actually dynamic programming by creating cache or memoizing the values, because recursion itself is not top down. So when you go recursion plus caching the values, that's the dynamic programming. But again, the true for some dynamic programming is this, right? The bottom up approach. So here is my second problem, trying to understand the concept behind, right? Because most of the videos out there are focusing on solving the problem using the technique, right? The technique is almost always the same. You create a DP array, is most of the times up to n plus 1, being n the number of items in the array, or the stairs here, the steps. So most of the time you will find that is plus 1, so compared to the input. So the logic behind is you need to iterate through that array you build with, you most of the time fill it with zeros. And I'm not going through that here because you will find that very clear in some videos. I just want to try to help you understand how you put values here, not in a computer way, but just in a logic way. So, for example, for the climbing stairs, again, we're going from the edge case all the way to the end. So what is the deep, this is DP, is dynamic programming. So we will build this array, we'll fill this array with all the combinations we have up to the number of steps. This, in this case, example is 5 steps. Here's the first thing that I had problems to understand. Let's say that this is the best case, right? And you can associate the steps with the number of ways, which is this problem about to get to the step. That's why I put here a 0. So you say to get to the bottom, I don't have to take any steps. So you must say, okay, 0. But that's not about the how many steps, it's how many options or ways you have to get to that point. So if you are in the 0 floor, how many options you have to get to the 0 floor? It's just one option, just doing nothing, right? So here is not 0, it's 1. It's the options you have. So now you are in the you're gonna go to the first floor. How many options you have to get there? Just one. It's just by making just one step, taking one step. So here you put another 1, right? Now this is the most important part. So here you need to get to the second step. So forget about this. To get to the second step, you have 2 options. You can go either 1 step and then another step, or you can go all the way from the bottom to the second step, because you have 2 options, step by step or each 2 steps. So that's easy to understand here, right? The logic behind is pretty simple. But how to use this, because we are accumulating the number of ways we can get to a specific step up to that step. That's this array 4, right? So here, to get to the second step, I have 2 options. I can keep going with the option with the number of paths I had to the previous step, so step 1. So I know that to get to the step 1, I had 1 option. So that's 1. But I can also go with the option that I had 1 step even back, so like 2 steps back. In this case, when I was in the floor, I'd also have the option to go all the way from 0 to 2. So I'm here in the present, taking advantage of the information in the past. So here is the past, and this is the dynamic approach. So you are making decisions based on the past information you have. So that's why you say, okay, I can continue with the path I had to get to the first floor with 1 step, or I can also use the path that I had previously from the bottom, which is this one. So that's when you say plus 1 is 2, right? So to get to the second floor, you have 2 options, is 1 plus 1. And you can keep doing this just like the automatic way. It's just going, every step here is the sum of these 2 here, which is very similar to the Fibonacci series. But I don't want to get you to that mechanical usage of this. It's just trying to understand the why. Again, to get to the step 3, I have 2 options. from the previous information, from just the one step behind, so the step number 2, right? I was there and I had 2 options to get there. So I'm gonna go one step from here. So I'm gonna keep the initial options from one step back, just one. But I can also use the other option 2 steps back, which is this one, right? From the step number 1. So that's 1, right? Now we have 3. But this is the why, is because I'm using the past information. And so you can see, you can say why, but why are you creating more options if you're just going through the same stairs? So it's just going one step or 2 steps. And here's not very clear, but let's continue here. So if I do the same here, you're gonna have 5, right? But you say, why 5? I don't get the point. Why 5? Just imagine that you can, up to here, up to the number 3, you have 3 options. So those are different. So you can go from the 0 to the 1 to the 2 and to the 3. You can go from 0 to 1 to 3. Or you can go from 0 to 2 to 3. Right? That basically 3 options you have. When you go to the number 4, you are creating 2 more options, right? 2 more options. You can have the 1 step more or 2 steps more, right? So you add those combinations here, you have 5, because you're keeping the previous option you have, and you are adding 2 more options to get there. So, and same here, when you go to this, you say, okay, I can continue with this option that I have, right? And I can also use the option that I have here and jump 2 steps. And here I just want to jump 1 step. So these 2 options that's why we have 8, right? So this is fairly easy because you don't have to go through many options, just 2 options. But this is the case for the scares. What about the house robber, right? This is a little bit more tricky, but the concept is basically the same. So here, for example, which are the best cases here? These are the houses you have, right? If you are before starting, so you are before the previous house, so that's the DP0. This is when you go to the first house, which is the maximum amount of money you can have if you are in the first house, right? If you pass by the first house and you enter that house, how much money you can get up to house number 1, number 2, number 3, number 4, and number 5, because we have 5 houses here. Each one has money on it, and we need to maximize the amount. So this problem is about maximizing the amount, right? So, and the problem here is that the constraint you have is that you can't rob 2 consecutive houses, because that will call the police. So it doesn't mean that you need to go 1, 9, 2 or 3, 5. You can go 1, 5 if you want, that's it. Or you can go 3 and 2. In this specific case, is pretty straightforward. You go 1, 9, 2, and that will be the maximum, right? But I'm just using this because that's a bad example from lead code, but it shouldn't be this one. But either way, so in here we have how much money, sorry, can we get from the house? Zero. So we don't have any house, so we can't get money because there are no houses. Money is not a house, so we start with the base case is 0. So now to the first house, how much money we can get? Just that whatever is in the first house. If this is a 2, we're gonna have a 2 here. Those are our base cases. We're going to initialize our DP array with zeros, and then we're gonna change the DP1, which is the money, whatever is here in the first house is gonna be the value here, right? So here is the hard part. So you need to go by the house number 2, not entering yet. You need to decide, should I enter and get the money, right? Or should I skip it? But the thing is, up to here, it seems like you already made a decision, right? But this is helping you to track previous information to decide which is better. And it's gonna be always like 2 steps in the future, if we can say. Because when you go by this, by the way, in the way this is, the dynamic programming array is created, when you compare to the input, I is always one step behind, so I minus 1. So it's always going diagonal, right? That's something that I also should explain. I'll do it right away. So it's just to make things like easier. So you can iterate the array, the input array using a different variable. You can create a counter for that, but it's just convenient because you're always gonna loop the DP array. It's easier just to reuse the I or the counter, the variable you're using to loop, and decreasing by 1 just to get to this value here. So, but you can create another one and increment it out a little bit. That will be just more work. But that's the way it is mostly used in everywhere. So when we pass by house number 2, we can say, okay, should I skip it? If I skip it, it means that I'm gonna get the money that was before, so the house before, or I'm gonna take that money plus the money that I have 2 houses back, so I don't get the police and arrest me. So this is this is the present, and this is 1 decision back, and this is 2 decisions back. So the current house is always going diagonal back, like this. So the money at the current house is 3, right? So what is better? To use 3 plus whatever was in 1 house, 2 houses back, which is this value. In this case, no money. What is the maximum between the current money I have in the present, which is 3, plus the money that I had 2 houses back, which is 0, or the money that I had in the previous house, which is always in here. So it's 1. So what is the maximum? In this case is 3, right? So this goes here, 3. And let's do the next example. Now, again, this is the present. and I will care about 2 houses back, 2 decisions in the past, two steps back in the past to make a new decision. So this is the money that I can get in this current house, 9. Is 9 better than the money, 9 plus 2 houses back, better than the money that I had in the up to the previous house, which is 3? So is it 9 plus 1 better or greater than 3? Of course it is. It is. And how much one is that? It's 10. So again, up till the house number 3, the max I can have is 10. But we don't know what is in the future, and that's very important. Just pretend that here we have a 20. And we just made a decision here. I decided to get this previous house to get 10 because it was better than the other option. But I didn't know that I had a 20 in front. That's why we always carry 2 houses, because we can always change your decision. Okay, I decided wrong. I'm gonna go 1 back, this one, so I can get this one because it's greater. Let's keep the 20 there. So this is the present. I'm gonna say, okay, is it better to get the current house plus whatever I had before, 3, or the money that I had in the previous house? Of course 23 is better. So even though I had made a decision here because it was greater, I just changed that decision because I'm tracking 2 decisions back. So that's the beauty of this approach, right? And so finally here, I'm gonna do the same. Is it better to keep the money I had, to get the money that I have in this house plus the one that I had before, or keep the money that I had in the previous house? 23, of course, 23, right? So at the very end, I'm gonna skip this house because I already took this one. And because I took this one, I didn't take this one, but I took this one. And I'm just going back in the logic, so you can see that at the very end, it will work the same way you will do it naturally. So you will pick 3 and 20, and that's the solution, 23. Okay, let's do lead code. Let's do lead code number 91, which is decode ways. So again, we're trying to find the number of ways we can decode a string. We have 2 constraints. It's basically, or 1 constraint. It needs to be a valid code, right? The codes are from 1 to 26, but without starting with 0. So every time we find a 0 to start the character, even if it's 2 or 2 characters, it won't work. So we need to stop the decision we have made up to this point. We need to discard that path because it's not valid. It won't have a way to decode it because there's no code for anything starting with 0. So in here we have something similar to the climbing stairs. To be honest, here is kind of weird. Sometimes the problem itself will tell you that decoding an empty string is the option is 1. So there's one way to decode an empty string, or in sometimes it's just to make the math works. So for example here, you need to say the base case with an empty string is one way to decode an empty string. Just take it like this. And to decode one, the first character of the string, we also have one option, if, only if, is not a zero. That's why we need to have a conditional to return with a zero if the first character of the string is a zero. No matter what if it's after that, if it starts with zero, it's not valid. It's impossible to decode the whole string. So again, so we have this for the solution for this, we'll start the loop in here because we already filled the two first position with the base cases. So you will go like this. This is always the same, right? To the present, I can have to fill up to the second position of the array. I can have only this. Is one valid? Yes, because it doesn't start with zero. So I have this option, but I can also have two characters as a valid option because 11 is valid. So I have two options. But again, this is the logic behind. But how the TP array help us is by just summing the previous two options. But then here's the why. So why you sum this? Because up to this point you were here, and you know that you can use that many options up to one step before. But also imagine here you have, this is the solution for two steps behind. So let's imagine, let me go one character more so I can show you better. So here we have two. Okay, now here we are in the present, so we need to look here back. So we have two options. Taking one character, which is valid, so that means that I can keep going through that path because still valid. So I can carry whatever I have here, which is the solutions to up to the previous step. In this case is 2. And let's see if I take 2, still valid, so 11. So that means that I can carry this value here. But why this value? Because this was the solution when I was in here up to this point. Up to this point I have this, right? So if I'm here and the next decision that I make is taking these two, it means that whatever number of options I have up to this point, which is 1, I can continue with this approach because still valid. So it means that up to here I can go with the double digit and with one single digit. That's what I'm adding, these two different paths. And I have here the number 3. Okay, now things became like more interesting. So now here in the present, I'm gonna look this way. up to this point. So what happened if I take this last character, just one? It's not valid, it's a 0. So we know that we can't continue the path we had up to this point and adding just one character. That means that this solution, this solution that we have here, it is not valid because the previous decision that I made, that was just including this one by just one, increased this number of solutions here. But because I made this decision, the next decision that I had to make right now in the present is not valid. So that means that this is not possible. And let's see what happens if I take two numbers. 10 is valid, so I can get this value I have here, but I can continue with the path that I had up to this solution when I took these two and then I took these two, right? And also the ones that this is 1, this is 2. So in here we know that we cannot use this one, right? So it means that we are discarding one of those options, right? But we are only taking this plus this. It means that we go back to 2, the number of ways we had previously before making the decision of taking this unique character, the 1, right? Now, but at the end, I'm looking here, so can I have this number? Yes, so I'm keeping this up to here. Can I have this? No, because it starts with 0, so this is not valid. That means that I can take whatever was before making this decision. I mean, when I was here. If I am here, I can't go 1 and I can't go 2. So here the final answer is 2. There's 2 ways to decode it. One way is going, I'm gonna picture it here. One way is doing double here, and 1. That's one way. And the other way is going 1 here, 2 here, and 1 here, right? It's not the numbers of encodings, it's the different paths that I have to decode it. And I'm going to show you why those are the only ones. Let's say I start 1 and then I got 2, then the next step is going to be either 0 or 0, 6. None of them are valid, so this can go. The other is starting with 2 and then 1, and then the next step is going to be either 0 or 0, 6. Still not valid. So that's why the only 2 valid options are the one that I show you. But the thing again here to understand is how can we get advantage of this, so we are not creating a bunch of combinations to iterate and just make a decision with a brute force approach, creating all the decision tree and going all the way down, even if we can cache the results. With this approach, the dynamic approach, you are not creating all that stuff. So you are just making decisions in the present based on the decisions you make in the past. In this case, because the problem is basically making you to take two decisions, to make two decisions. You can encode one character or two characters if they are valid. So that's why you are tracking two steps back. And the result of the present is not zooming, just like in the previous examples, is deciding if you can keep the decision you have made one step back by taking the next decision, and if you also can keep the decision you make two steps back by making the present decision. So this is a very good problem for the users of dynamic approach bottom up. Okay, so finally we have the coin change problem 322 bit code, and I really like this one because the difference with this one here is that you don't have two options to make. You have up to n options to make. Why? Because the problem gives you coins and you can reuse them as much as you can. So you need to be smart enough, because if you go with a top-down approach and create a recursive approach, you will create a decision tree and you will create a very, very deep tree all the way to the bottom, reusing one coin, right? And even though you can use the dynamic approach by just creating some cache and store those results, it is still less efficient than going dynamic approach bottom up. So basically here we have the base case is this is the amount, right? We are using the dynamic programming array to keep the minimum number of coins we can use to get the amount we have in this position. So here is $0, $1, $2, $3, $4, $5, all the way up to the number of the input in the example. In this example is 8. So we need to know which is the minimum number of coins. We don't need to track which coins, but the number of coins, the minimum combination we can come up to get $8 using these coins. Remember, you can reuse one coin as much as you want. So for example, you can use 8 times $1 to get 8, but that will be probably the longest combination you can come up with, right, for this example. So here, one very, very easy base case. How many coins you need to get $0? Easy, 0, right? So in this case, we are looping our dynamic array starting on I in the first position. So not first position, the index 1, which is the second position. And it's pretty much in this case, because we are not going through the input array, which is the coins, in the same way we did it before, we are free to reuse. So this approach is different. You will have two loops. One loop outside is going to be moving the index for the dynamic programming array, and inside of that loop, for every position here, which is the amount, you need to find the minimum combination you can have to get to this amount. So that's why to get 0, you need 0 money, zero coins. Now, to get $1, just to get $1, which is the minimum combination of these coins here to get $1. For this example, luckily we have one coin of $1. That means that I can use this coin and that's it. If I use 2, 5, 4, and 3, I'm getting out of bounds, or meaning I'm getting more the amount that I need. So these options are not valid. So inside the loop, the inner loop, you will do something like which is the minimum of using the coin number 1. But that will, okay, easy. That's like a brute force. Yes, correct. But here's how you can get advantage of the information you have stored in the past, and I'll show you how. I'm gonna skip the first one. It's just 1. Okay, now to get 2, right? To get $2, so you start the loop. Okay, I can have, I'm not taking n monies, n coins every step. I'm taking just 1 coin, no matter the value. So I'm gonna use this coin $1. Okay, so if I get $1, how much left do I have to get to the amount? Okay, that's 1. Okay, and here's the thing, we already know how many coins is the minimum combination we can come up to get $1, right? So we have this, to get this is 1. Okay, so 1. So the coin that I'm taking is 1, plus the solution we already know is 2. Easy, you know, right? If I use a coin of $1, I need 2 coins, right? This is easy to come up by thinking, but how you put that into code. So that's why this is very powerful. Not good, but is that the best option? Let's see. We have, let's take the coin number, the coin of $2. So 2. How much you have left to get to $2 in here? I'm sorry, yeah, to here. $2. 0, right? And which is the solution for 0 coins? We already know that solution is 0. So that means that is 1 coin, sorry, here is 1 coin of $2 plus 0 coins is 1. If I get the 5, 4, and 3, I'm gonna get out of bounds. So for this case, getting an amount of $2 with these coins, the minimum combination is using the coin of $2. So that's 1. Sorry. Let's continue with the example here. Okay, now I need to make $3. Again, I'm already iterating to the next index of the array. I'm index 3, right? Which means $3. I need to get up to $3. So I'm gonna start iterating my loop of coins. I'm gonna get the first one, $1. If I get $1, how much do I have left to get to 3? 2. Do we know the solution for 2? Yes, it's here, right? So I say this is 2, which is 3. If I use the coin, sorry, this is 1. My bad. if I use the coin of $1, the best combination by using the one coin as the first option is then using the coin of $2. So that's why I have 1 plus 1, right? And so now let's move to the number 2. So how much do I have left? 1. Which is the solution for 1? Is 1. Right? So here, this is important. This is not a plus, this is a 1. And every time that I use a coin is 1. This is the 1 coin and this is the 2 coin. But it's just using 1 coin. And the solution for 1 coin left is 1. So it's, again, 1 plus 1 is 2. Now, I'm gonna get 5. It's gonna be out of bounds. I can't use that. 4 is gonna be out of bounds. 3. So 3 is gonna be, again, 1 coin of $3. How much do I have left to get to amount, which is 3? 0. The solution for 0 is here is 0 coins, right? So 1 plus 0 is 1. And that's easy, right? You don't need more money. You don't need more coins to get $0 that are left. So the solution for this is 1. The minimum combination to get $3 is using 1 coin, the coin of $3, right? Now, we have 4. So, with 4, we're gonna loop. We're gonna have 1. What we need to get to 4 is 3. The solution for 3 is 1. So if I pick 1, a coin of 1, I will need a coin of 3 to get 4. So I need 2 coins. So that's 2. If I pick the number, the coin 2, I have 2 left. And the solution for 2 is 1, which is another coin of 2. That's, again, 2. If I pick 5, I'm out of bounds. If I pick 4, what happened? I will have 4, and I have 0 left. 0 left needs 0 coins. That means that I can get up to 4 with 1 coin, a coin of 4. So that's 1, right? If I use 3, I will need 1 more dollar, and to get 1 more dollar, the best solution is 1, so it's gonna be 2 coins. So at the very end, to get $4, I need 1 coin. So that's the minimum, 1. Okay? And so that continues, and to get 5, I will get to the same point that I need just 1 coin of 5. That will be the minimum solution. If I get to 6, there are different options. I can have the coin of 1 and I have 5 left. The solution for $5, the minimum combination is 1, a coin of 5. So if I pick 1, then I go pick 5 and I have 2 more coins to get to 6. And it will do the same with 2 and 4 and 3 and 3 and 5 and 1. We don't care about the combinations. We just care about the minimum combination. And I have 4 different combinations or 5 but they are all 2. We have another way. We can have 6 coins of 1, 3 coins of 2, but we don't care about those. So the minimum solution here is 2. If we go 7, again, we'll have 1. I have 6 left, and for 6, I need 2 more coins. So it's gonna be 3 if I pick 1. With 2, I will have 5 left, and the minimum combination coins that I need for 5 is 1, so that makes 2. and if I click 5, I have 2 left, and the minimum coins I need to for 2 is 1, and so it will be basically the same here. So the minimum is gonna be also 2, right? Now this is gonna hold the answer, because this is the amount that I'm asking. This is the problem, right? So the last position of the DP array is gonna have the answer, right? So in here, I will pick the 1, right? I have 7 left, and I know, okay, for 7 I need 2 more coins, so it's gonna be 3. For 2 I have 6 left, again 2 more, 3. If I have 5, I have 3 left, and I know that I have 3 left. I can get it with just 1 coin of 3. So that's so far the best, with 2 coins. If I pick 4, I have 4 left, and I can also have 8 with 2 coins, 2 or 4. And if I pick 3, same. When I have 5 left, which it can get to 1 coin or 5, so I have 3 different options to get to 8 with 2 coins. So this is the answer, 2, right? So here the difference with this problem, we are not going back 2 positions or 3 or whatever. We are just storing in the DP array all the subproblems we solved before, so we can access them. And just imagine we have all the decision tree that will go like the right side, you go all the way here in the left side, and then you will create the repeated work, just $1 less. It will create from 7 to 6 to 5 to 4, and it will always go repeated, because it will, that part is already solved in the left side. So, but we are not even creating that. It's already solved in this accumulation that we have of minimum solutions, and we are not zooming. We are always making a decision, but using information we have from the past sub-problems that we solved. So that's it, my friends. Again, this was my first video. Sorry about my mistakes, my spelling mistakes, and whatever is confusing, just leave me comments. I'm not saying that I'm gonna create another video, but probably, I don't know, who knows. But yeah, so this is all about making it like more logical thinking instead of programming and coding. Is how can you identify the problem, because you won't have always the in the problem, in the question, it won't tell you, okay, this is a dynamic program, bottom map or top down. You need to identify that the problem you are trying to solve can be solved using this. And most of the time you will find that those problems are because you need to make decisions, right? You need to make decisions, and those decisions are repeated. So you solve a problem, you might have the same question or the same situation in the future of the solution, so you can reuse that previous solution to the new solution. That's one option, like this one. But sometimes, like here, you need to move forward, making a decision based on what you did just right in the past. One step back, 2 step back, like this one here. So it's very important to understand that they solve the same situation, which is avoiding repeated work, and using loops, but they are not always used the same way. Because, for example, these three options here, these three problems, they have the dynamic approach, and you actually can code this right as it is. You can create these arrays here, and that will be your solution, and you just need to return the last value in the array, right? But you are always tracking in these three problems, you are always tracking two values behind. So you don't really need to store an array. You just need to create two variables that are initialized with the base cases. Yeah, you can call them pref and pref or 1 and 2, whatever you, it's more related to the input or to the problem. Like, for example, here, previous step and prev step, prev house or prev house, or house before, house prev before. It doesn't really matter, but two variables you can use, and you just can't forget about the array and just keep modifying those two variables, because you only care about two values before the present value. But in this one, it's not like that, because you are not tracking the value exactly right behind. It's tracking just whatever is in the array based on the amount you have left. It can be here, here, or here, right? So in this case, the memory optimization is not straightforward. At least I don't know how to convert this problem as I explained this before, because they will go from memory complexity of n to constant time, to constant memory O1, but this one here can't go like that. It's different. So that's important for you to understand as well. And that's it. I hope this was helpful for you. Just leave me some comments, and you can also say, hey, just quit and forget about explaining. This was messy, or maybe I did something good for you. Thank you.